Hello everyone, this is Sohit.
This is Vinay Kumar.
Today we are going to discuss about dynamic branch prediction in RISC-V. So let us discuss the contents. So first of all, why do we require this branch prediction? What are the kinds of the branch prediction? I mean, basically, what are the schemes? And then lastly, we'll see about the verilog implementation and then the simulation results. So why do we require this branch prediction? So generally, the outcome of a branch, whether it's branch equal to or branch greater than or less than, is determined in the execute stage, which is the third stage of the RISC-V pipeline. So, waiting for that results requires two NOPs, or if you say two stalls. So, stalling for every branch hinders the pipeline processor speed. So, generally the microprocessor, there are millions of instructions. So, waiting for every branch instruction, I mean, having two NOPs for millions of instructions makes the processor slow. So, to avoid this, we are going for the branch prediction. So let us see about what are the kinds of branch prediction techniques. So generally there are two kinds. One is static and then the other is dynamic. And in the dynamic there are two again, which are local and global. So let us discuss in detail about these. So the first is static branch prediction. So as the name suggests, the static branch prediction is the branch is taken or it is not taken. It is always taken or it is always not taken. So you can see in this slide, the first thing is branch taken scheme. So in this branch taken scheme, it is always predicted that branch is always true. So if it is true, there is no problem. Else, if it is not true, the instruction which is fetch has to flush, and then it has to refetch again. So that is one of the scheme, and the next scheme is branch not taken scheme. So in this branch not taken scheme, it is always predicted that the branch is always false, and it goes to the next immediate instruction, as you can see here, since the branch is false. So if the prediction is true, there's no problem. The execution stages goes on as usually. But if at all if at all it is false, then the instruction which was fetched has to be flushed, and then the branch address has to be fetched again. So this is static branch prediction. So this is not mostly used. So since there is no, there is no history. There is no track of history. So that's why we go for dynamic branch prediction. So before going to this dynamic branch prediction, let us discuss about the branch history table. So basically, this branch history table is just like a memory which keeps on the track of the previous branches. I mean, the outcomes of the previous branches. So here we are. I mean, in this verilog implementation, I'm using eight location branch history table, and each location has either 2 bits or 1 bit. So first we'll discuss about this 1 bit prediction scheme. So in this branch history table, initially you can fill all the locations to 0, which indicates that none of the branches are taken. So whenever the PC sends out the address, so the last 3 bits are taken to see the branch history table. If it is 0, it means that the predicted outcome is not taken. If it is 1, the predicted outcome is 1. So here you can see a simple FSM. So if a particular entry in the branch history table is 0, it means that it is not taken. And if in and the actual outcome, mind you that actual outcome comes in the execute state. So in the execute state, if the actual outcome is also not taken, which is exactly same as the predicted outcome, so it remains in the same state. So if at all the outcome is taken, which is against the predicted outcome, so it shifts to the predict taken. The 0 is replaced with 1. So again, if the same location is accessed again, uh, uh, it assumes that the branch prediction is taken. So and in the execute state, the actual outcome comes. And in that outcome, if the branch is taken, it remains in the same state, or if it is not taken, it goes into the next state. So in this, the disadvantage of using 1 bit prediction scheme is that there is only 1 bit which is toggled every time the outcome is come. So So that's why we're going for 2-bit prediction scheme. So in this 2-bit prediction scheme, there are two kinds. There are two approaches. The first one is saturation counter, so which we have implemented in this project. So in this saturated counter, there are four stages: 0, 0, 0, 1, 1, 0, and 1, 1. So 0, 0 indicates it is strongly not taken. 0, 1 indicates it is weakly not taken. 1, 0 indicates it is weakly taken, and 1, 1 indicates strongly taken. So similarly here also there is a branch history table. Unlike the 1-bit prediction scheme, in the 2-bit prediction scheme, each location has 2 bits. So it can be 0, 0, 0, 1, 1, 0, and 1, 1 like that. So when the branch instruction comes, the corresponding address, those bits are used as an index for this branch history table, and the corresponding location has 2 bits, so which determine whether the predicted outcome, whether it should be taken or not taken. So let us suppose the branch history table, the outcome of the branch history table is 0, 0, in the sense it is strongly not taken. So in the execute state, the actual outcome comes, and if that actual outcome is also not taken, then it remains in the same state. If at all the actual outcome is taken, then it goes to the 0, 1 state, next state. So in the 0, 1 state, there are two again possibilities whether the branch is taken or not taken. If it is taken, it goes to 1, 0 state, which is weakly taken. If it is not taken, it goes back again to the 0, 0, which is strongly not taken. So this is called a saturation counter because every time the outcome is false, it goes from 0, 0. 0, 0, 0 indicates that the predicted outcome is not taken, but if the actual outcome is taken, it goes to 0, 1. So 0, 1 indicates it should not be taken. If at all the actual outcome is taken, it goes to 1, 0. And in the 1, 0, the predicted outcome is taken, but and if the actual outcome is again taken, it goes to 1, 1. So it is called saturation counter because it goes from 0, 0 to 0, 1, again to 1, 0, again to 1, 1, and in 1, 1 state it is always in the 1, 1. So it is called saturation counter. And likewise, if at all it is not taken, it goes from 1, 1 to 1, 0 to 0, 1 and 0, 0. So it acts as an up-down counter. So this is one approach for 2-bit prediction scheme. And then the other approach is it's a 2-bit prediction scheme, but the only difference is that from strongly not taken, it goes to weakly not taken, if at all the outcome is taken. And again, and in this 0, 1 predicts it should not be taken, but if the actual outcome is taken, it goes to strongly taken, which is 1, 1. Unlike here, it goes from 0, 1 to 0, 0, 1, 0, which is from weakly not taken to weakly taken. But in this scheme, it goes from weakly not taken to strongly taken. So this is the only difference from these two approaches. So we have implemented this saturation counter. So let us see an example of this 2-bit prediction scheme. So let us say at the address 0, there is an instruction called add x17, x17, 1. So this indicates that the value in the register R1 has to be added to the value in the register R17, and again it has to be stored in R17. So let us assume that R1 has a value of 1 and R17 has a value of 17. So these two are added and the value 18 is stored in R17. So let us suppose this is the first instruction. So, and in the address 12, so there is an instruction, branch equal to x17, x18 and 28. So this instruction states that it compares the register x17 and x18. If these two registers are same, then the PC values jumps to PC plus 28 if this instruction is true. So let us see. So the 12 is represented as 0, 0, 1, 1 and 00. So these two LSB bits I am neglecting because in RISC 5 the LSB2 bits are neglected because the instructions are in the multiples of 4. So I'm not writing 0, 0 everywhere. So the 12 you can write it as 0, 0, 1, 1. Since the branch history table has 7 locations, the last 3 bits of these 3 bits are used as an index to access this branch history table. So since this address is 3, so it goes